In the last video, we learned about various types of chemical reactions. We learned about synthesis, which is when things come together to make something larger, decomposition, when something breaks apart, single replacement, where one element will take the place of a less reactive element, double displacement or double replacement, where two things swap partners, and combustion, where you have a hydrocarbon reacting with oxygen to make carbon dioxide and water. And now in this video, we're going to take a look at balancing some of these equations. So I've put three different examples up here, one that's fairly easy, and then a couple where I have a little bit of advice for you that might not be standard. So in the first equation, you can see that you have phosphorus as P4 reacting with iodine, which is I2, to make phosphorus triiodide. So you can see clearly that you have a different amount of each element on both sides. So what I like to do is make an atom inventory, which will help keep track of how many of each element or each substance we have on each side. So on the left side, you can see that there are 4 phosphorus atoms. On the right side, you can see that there's only 1. And following the law of conservation of mass, atoms aren't just going to disappear or come out of nowhere. So we've got to make sure we account for all of them. So you have 4 phosphorus on this side, 1 on this side. I have to put the coefficient 4 here. That will tell us that if we have 4 of these molecules, we would have 4 atoms of phosphorus accounted for. So now phosphorus is balanced at the same amount on each side. Iodine, however, now, if I have 4 molecules of Pi3, that means I'm going to have 12 iodine atoms to account for. So in order to balance that 12, I have to put the coefficient 6 here to make it so that there's the same amount on each side. Now, everything's accounted for. We have a balanced chemical equation, and this would be a synthesis reaction. In the next one, we have a double replacement or double displacement reaction, where you have aluminum hydroxide reacting with carbonic acid to make aluminum carbonate and water. And you see something with hydroxide, which is qualified as a base. I like to take water, and instead of writing H2O, I like to write HOH, where the first hydrogen usually would be represented by the acid, and then the hydroxide from the base. And that'll help you look at those things separately so you can balance it a little bit easier. So let's start with the other things and then worry about those. First, I see that I have 1 aluminum on the left side, and I have 2 on the right. So in order to balance those, I have to put the coefficient 2 here. Now, I look and see that that means I have 6 hydroxides, because if I have 2 of these, and each one of them has 3 hydroxides, that's a total of 6. So that means I have to have 6 hydroxides on the right side. So I'm going to put the coefficient 6 in front of there. So at this point in time, I have 2 aluminums on each side, and I have 6 hydroxides on each side. Those are balanced. Now, I look and see that I have, let's just look at carbonate next. So I have 3 carbonates over here, and only 1 on this side. Now, notice I put carbonate as one thing in here, and I do that only because it appears the same on both sides of the equation. So rather than looking at it as carbon individually and oxygen individually and confusing it with the other ones, look at it as one thing, and it makes it a little bit simpler for you. So again, 3 carbonates on the right, 1 on the left. I'm going to put a 3 right here, and that means I have 3 carbonates on each side. And now we look to check to see if the hydrogen's balanced, and let's hope it is, because otherwise it screws everything up. I have 6 H's on the left side, and then 6 of them on the right side. So now you can see we have a balanced chemical equation for this reaction. And lastly, sometimes when we're balancing, in particular combustion reactions, we end up with not quite a whole number ratio at first, but I'm going to show you a little trick you can do to account for that and get it so it's a balanced chemical equation with whole number coefficients. So if we look at the combustion of gasoline, or octane rather, you have C8H18, so there's 8 carbons on the left and only 1 on the right. So to account for that, I have to make 8 CO2s. So if you have octane combusting, those 8 carbons would be found as carbon dioxide in the products. Then we look at the hydrogen. You can see there's 18 on the left. So what do I have to multiply this by? 9 to get it to 18 on the right. So now you can see that I have 8 carbons on each side. I have my 18 hydrogens on each side. And now let's look at the oxygen. Anytime you're balancing an equation and you have an element that's by itself, save that one till the end. Because what happens is if you change this one early, anytime you change anything else, it's going to adjust this anyway. So you can change this without impacting anything else. So now I look and I see that I have 16 oxygens on the right, there with the carbon dioxide, and then 9 more. 16 and 9 is a total of 25. So if you look over here, like, well, there's no whole number you can multiply that by to get 25. So you could put 12.5 there, but you would have to do something else to fix it. and this was an understood 1. Now, anytime you have a 0.5 in here, if you want to get everything to whole numbers, you can just multiply all of them by 2. You'll have the same ratio, however, you'll have them in whole numbers. So this 1 becomes a 2, the 12.5 becomes a 25, the 8 becomes a 16, and the 9 becomes an 18. And at this point in time, if we do our atom inventory just to make sure we're good, I have 16 carbons on the left, I have 16 carbons on the right. I have 36 hydrogens on the right, 36 hydrogens on the left, so that's good. And at this point in time, I have 50 oxygens on the left, and I have 16 times 2 is 32, plus 18, I have 50 on the right. So now you can see you get a couple general strategies you can use for balancing chemical equations, and this basically lets you follow the law of conservation of mass, showing that no atoms get created or destroyed in a chemical reaction, they just simply get rearranged.